And share screen. All right. I'm gonna start with linear elasticity today, and I'm gonna cover hopefully a lot. I guess quick announcements. Lab exam on Friday, and then we'll send an announcement today. But basically, it's gonna be open throughout Friday, but highly recommend to show up to your assigned lab section because that's when Tina is gonna be in the lab. And also because there's other hours in the day where there's other classes or the lab is occupied. So for sure, it's gonna be free, from 9:30 to 1:30 for your assigned lab section. So I highly recommend that maybe if you want to take a look at it when it's posted, it's gonna be posted ahead of 9:30 a.m. So you could take a look at it, but I would say show up during your lab section. It should be doable within the 2 hours of your lab section. Any questions? That's the main thing for this week, I think. It's gonna be up. I don't know about that.
It will be like the 2 hours.
So it's gonna be open for 2 hours.
Yeah, just like the.
Okay, it's gonna be 2 hours, just like this. So recommend that you show up for your assigned lab section because that's when Tina is gonna be in the lab. Any other question? All right. So another thing, I uploaded the video and the Python code for the quadrilateral heat transfer problem. I actually solved it. Finished. In class, I had done the stiffness matrix and the force vector, and I just finished that in the Python notebook, and I uploaded that to PL6. I know this is technically PL kind of 5.5, but I uploaded it on their PL6. All right. So today we're gonna start with linear elasticity in 2D. And as usual, we need to define the strong form and the weak form because that's what, the weak form is what Abacus solves, for example. The strong form of linear elasticity is actually two equations. It's sort of two scalar equations or one sort of matrix equation. So in the book, it's written as these two. The equivalent is just the divergence of the stress matrix plus the B vector equals the zero vector. So if it's written in that form, this basically is vector equation. Because this has two components. X and a Y component. You can, in the book, for example, you can explicitly write down the two equations. So these are, each of these is a scalar equation that looks just like heat transfer problem. And that's why the book does it like that. So this is one of the equations that you need to solve, and this is the other equation that you need to solve. And you can see that this is basically same as the heat transfer. Where is the divergence of some vector. The sigma x is the vector of x forces or x stresses plus bx, which is just the body force x component. And this one is also same as heat transfer. Same structure. I mean, it has a different meaning, but it's the same structure. So again, in other words, the elasticity problem is basically solving two heat transfer type problems at the same time. And if you want to think of the analogy between heat transfer and force balance, in heat transfer, what is this term? The divergence of what? in the heat transfer problem is divergence of something plus something, divergence of the flux, which is the gradient of the temperature. So this sigma x is, so the x vector of the stress tensor or the stress matrix is basically flux of forces. You can think of this as sort of flux of forces for the x direction, flux of x component of the force. And this bx, you can think of it as a source of forces, like gravity. And then this divergence of sigma y, you can think of as sort of sum of forces in the y. And then you want basically, when you say divergence of the entire thing, you want both that the flux of forces in x balances out with the source of forces in x, and that the flux of forces in y balances out with the source of forces in y. So you can think of the stress problem as a combination of two heat transfer problems. Similar to the heat transfer problem, there is a relationship between the stress and the gradient of, not temperature, in this case is displacements. There's a little bit something special about this gradient, it's just the symmetric gradient. But you can see that this structure is similar to in heat transfer, we had this, right? So in heat transfer, we had the flux was minus the conductivity matrix times the gradient of temperature. Here we also get the stress is sort of proportional to, here stress is proportional to gradient of displacements. And then we have two types of boundary conditions. We have either essential boundary conditions, so you know the displacements. Or you have natural boundary conditions, meaning you know the flux or the forces, basically. Technically, they're called tractions. So again, the elasticity problem is the divergence of the stress matrix plus the vector of body forces equals the zero vector. That's the matrix equation up here. Or you can write it as basically two heat transfer problems. And do quotation heat transfer because it's not heat transfer, but the structure is the same. So divergence of this sort of x flux vector plus the x source term equals 0, and divergence of this y force vector plus the y source term equals 0. And then again, we need a relationship between the stress and the displacements. Not exactly the same as the heat transfer problem, but similar structure. The stress is related to the gradients of the displacements. And then boundary conditions, either flux boundary conditions, meaning forces in this case, or essential boundary condition, meaning displacements. So overall, the elasticity problem is kind of solving two heat transfer problems at the same time. Questions about that? All right. Now, as usual, Abacus does not solve the strong form of the problem. This one is, your PDE, And then what Abacus does is the weak form of that. How do we get the weak form of that? I'm not going to do the derivation for this one because it's a little bit more involved. It is in the book, but basically multiply the two equations by the weight function, sum them and integrate, and then do integration by parts, just like with the Green's formula, just like the heat transfer problem. Use boundary conditions. Again, the weight function should vanish in the essential boundary condition, and then you substitute the natural boundary condition. Note that the weight functions here, I'll just make that note. To go from strong to weak form. The weight function has two components, so it's a vector. So typically they will be defined like that. So W bar. So there's, there is an X component and there's a Y component. Just to keep in mind. And similarly for your unknown, the unknown is the displacement field. And then, because this is a vector problem, it's also a vector. So there is a UX and there's a UY. That has a consequence for when we set up the finite element problem, because again, this is like solving two heat transfer problems at the same time. We get twice as many unknowns. So instead of just having a single unknown, now we have all the X component unknown, all the Y component unknown. And then because of that, also the weight function should have basically an X component and a Y component. If you're interested in the derivation, I will not do it. You can refer to the book. But the weak form at the end of the day is find the displacement vector. So this U, which has X and Y components, satisfying the essential boundary condition. So it needs to satisfy U equals, how did I call it? U hat. It satisfies basically U equals U hat non-displacement in the part of the boundary that has the essential boundary condition. Then the integral looks like this. So the gradient of the shape functions times this D matrix, which is basically a matrix of material properties. Times the gradient of the displacements. Equals the integral over the boundary with natural boundary conditions of the weight function times the traction. Again, traction is basically the forces on the boundary. And then this is the force vector. So the integral over omega of the weight function dotted with the body force. And this has to be satisfied for all the weight functions such that the weight functions vanish at the boundary with essential boundary conditions. So the structure is very similar to the heat transfer problem. Again, you can see, I mean, there's a few differences because it's a vector problem. It's just a bigger set of equations, but the structure is the same. So gradient of the shape functions dotted with or times the matrix D, which has some material properties, times the gradient of the displacements. That gives you the stiffness matrix. Then on the right-hand side, we have the integral of W times T over the boundary with natural boundary conditions. That gives you the force vector of the forces at the boundary, and then the last integral over omega of W times B. That is the vector of body forces. Questions? All right. So given that is the weak form, let's see what I have in the next slide. Yes, so finite discretization. Before I go into the discretization, I'll sketch it out here. So what is it that Abacus is doing given that weak form? Well, as usual, we are going to introduce, if you remember our diagram, I haven't gone back to that diagram, but we have the strong form, then we have the weak form. So this is the weak form. Then down here, hopefully you remember, we have Fe interpolation. And then when you put those two together, then you get the system of equation. K U equals F. Which is what Abacus solves, this linear system KU equals F. So here, that's the weak form. Then what is the final element interpolation? So similar to before, we have the W's. What are the W's? The W's are just going to be the sum of the shape functions times the nodal values. The U's are also going to be just the sum of the shape functions times the nodal values. The gradients are going to be similar. So the gradient of W is going to be the sum of the gradients of the shape functions times the nodal values. And the gradient of U is going to be the sum of the gradients of the shape functions times the nodal values. So the interpolation is the same as before. The only difference is that these are vector instead of scalar quantities. So for the temperature, we had temperature was sum of shape functions times nodal values of the temperature. The weight functions in the heat transfer problem was sum of shape functions times the nodal values. Really, the only difference is that we went from scalar to vector, but the structure is the same. Just for notation, this gradient is a little bit special. It's a symmetric gradient. I haven't defined it yet, but it's almost like the standard gradient with some tweak to it, but it's easily calculated in a very similar way to the gradient for the heat transfer problem. So hopefully this looks very similar to the discretization of the heat transfer problem. Now, if you put this into the weak form, a little bit of space here. So you put this into the weak form. For example, what happens with the first term? The first term, which is the integral over omega of gradient W, and then times D times the gradient of U. Right, this is the integral, the first integral. So when you put the finite element discretization, and then we are going to do it for every element, what will happen is that I'm just going to substitute this I'm not going to do the whole derivation, but we basically substitute that, and then there's a lot of algebra. that will basically, just like we did for the heat transfer problem, take the sums out, take the nodal values out. So we're gonna end up with something like this. Gonna be something like that. So after doing the algebra, take the sums out, the nodal values out, and then what we are left with is the stiffness matrix for that element. So again, the structure is not exactly the same, but it should look similar to the heat transfer problem, right? So in the heat transfer problem, we had integral over, and it was gradient of Ni times the conductivity matrix times gradient of Nj. Very similar, the only thing that has changed is the gradient. This is a special gradient. So that one looks a little bit different, but aside of that, the structure is the same. How about the body force? So if you look at the integral is this. The integral of the weight function times the body force vector. So when you put in the finite element discretization, then you're gonna end up with here sum of Ni Wi dotted with B. And again, taking the sum out and the nodal values out, we're gonna end up with integral of Ni B. And this will define our force vector. And again, it looks very similar to the force vector for the heat transfer problem, where it was the integral of Ni times S. In this case, it's integral of Ni times P. So given the stiffness matrix for an element, given the force vector for an element, the process, what Abacus does behind the scenes is exactly that. So loop of elements, for every element, calculate this force vector, calculate this stiffness matrix, then assemble into the global K and the global F, and then partition the system using the essential boundary conditions and solve. Questions? Cool. Now, finite element discretization in 2D, we're actually going to define explicitly what Abacus is doing for some of the elements. I was saying the B matrix is a little bit different in this case because this gradient of this gradient S is a little bit different than the standard gradient. So to calculate the gradient of every shape function, actually what you, and this is because of the definition of the strain. So the strain has basically these three components, or the stress has these three components. So the XX component, the YY component, and the XY, the shear strain component. So this gradient is a little bit different from the gradient that we were using for the heat transfer problem. And if you put it in a matrix form, the B matrix has basically every column is the, so these two columns basically represent the gradient of N1. These two columns represent the gradient S of N2, and so on. And then depending how many nodes you have, this is the gradient S of N. Here is called NEN. So what is the size of this matrix? Well, if it is a triangle, for example, there's 3 nodes. So then this would be a 3×6. So for triangles, the BE is 3×6. For quadrilateral elements, at least the linear quadrilateral elements, what is the size of the B matrix for? 4×8. The 3 stays always the same, but 3×8. But it is, yeah, the 8 is because now you have 4 nodes, sorry, and every node has basically an X and a Y component. So it's going to be 3×8. At least for the linear quadrilaterals, if it was, the quadratic quadrilaterals, I forgot how many nodes the quadratic quadrilaterals has, like 9. So it would be 3×18. The quadratic triangles have, I think, 6 nodes. So then it would be 3×12, for example. So whatever the number of nodes times 2, that's the number of columns in that B matrix. And by the way, this we already know how to calculate. The individual entries we already know how to calculate because we were calculating this for the heat transfer problem. So as long as you can take derivatives of the shape functions with respect to xy, which we were doing in the lab on Friday, for example, then you can fill out the B matrix. So again, there's a B matrix that has components of the derivatives of the shape functions with respect to xy. It is a little bit different from the heat transfer problem for 2 reasons, because we have X and Y components. So now the B matrix has twice as many columns. And also because there's 3 different parts of the gradient that we're interested in, like this EXX, EYY, and the shear component. Given the B matrix, let me put one extra. So like I said, the stiffness matrix is what I had said before. So it's the integral over omega E of this gradient S Ni times D times gradient S and J and instead of expanding this out and do every single component, this you can use this B matrix notation. So this is BE transpose D BE. No, what happened? Matrix notation. Otherwise, for the heat transfer problem, I was actually writing out every single entry of the stiffness matrix. But for the elasticity, the problem is I have twice as many rows and columns. So then it gets pretty tedious to try to do every single component. So better do it with the B matrix. Times D. The D is a matrix with the mechanical properties. I'll introduce that below in one of the next slides. So quick question, what is the size of the KE matrix? For example, the triangular element. Yes. And again, this is because this is like solving two heat transfer problems at the same time. So there's an X and a Y component. And so this, when you do the assembly, this is sort of the first node X entry, and then first node Y entry, and then second node X entry, second node Y entry, third node X entry, third node Y entry. So that's why there's twice as many rows, because we have X and Y. For every node, we have an X and a Y. For the quadrilateral element, this would be an 8 by 8, because now we have 4 nodes, and for every node, we have an X and a Y component. For the force vector, again, if you recall what I was defining as the force vector is the integral of NIB. And then, for example, for triangles, this will be N1 with the X component of the force, N1 with the Y component of the force, N2 with the X integrals, all of these are integrals, N2 with the Y component of the force, N3 with the X component of the force, and N3 with the Y component of the force. So the force vector for the triangle is a 6 by 1. Again, because the first two correspond to the first shape function, so the first node, but X and Y components. So this is 1X, 1Y, 2X, 2Y, 3X, 3Y. For the quadrilateral, this would be 8 by 1. So the first two would be integral of N1 with either BX, BY, then N2, BX, BY, N3, and then finally N4. So given the element stiffness matrix and the element force vector, you can put them into the big stiffness matrix and big force vector, just like before. What you get is you get your usual system of equations. You can your global stiffness matrix, you can split it into these known displacements. Those known displacements have unknown reactions. And these are the unknown displacements. And for those, there's either body forces and or traction forces. So that FF will have body forces for any node, traction forces only for nodes on the boundary. The split of the system is the same as usual. So the solution would be also the same as usual. So KF inverse times FF minus KF transpose DE. That's it. So that will be the solution. Solution with the matrix partition. Any questions? Kind of flying over this, but I mean, we've done a lot of the details for the heat transfer problem. I don't want to overwhelm you with all the details for the elasticity one. I really want you to see that the flow of the things that we have done, in 1D and for heat transfer repeats for the elasticity problem with, a few variations, but it's the same idea. You have this strong form. In this case, the strong form is basically solving two heat transfer problems at the same time. Then you have the weak form. You introduce your finite element discretization. Again, the only difference with respect to the heat transfer is that now you're doing sort of two heat transfer problems at the same time. Once you plug in the finite element discretization, you do a little bit of algebra to take out the sums and the nodal values. Then you end up with the definition of the stiffness matrix and the force vector, which involves integrals of the gradients of the shape functions. Once you have the element stiffness matrix and elements force vector, you can assemble into the global stiffness matrix and global force vector, and then you can do your matrix partitioning and solve. So same flow. All right. So let's introduce one specific example, the constant strain triangle. So the constant strain triangle is the linear triangle. It's called the constant strain triangle because if you recall, for the linear triangular elements, the gradients are constant within the element. So then you don't have to do the integral. There's no Gauss quadrature involved. Basically, the integral boils down to just multiplying by the area. So when you do the stiffness matrix is still integral over the element of the B matrix times this D matrix times B. But because the gradients are all constant, this is basically just the area of the element times B transpose D B. Again, because the gradients are all constant, then doing the integral just means multiply by the area. And then what does that B matrix look like? I have it in the next slide. But if you recall what the definition of the B matrix was, it was dn1 dx, 0, dn1 dy, 0, dn1 dy, dn1 dx, and then dn2 dx, 0, dn2 dy. Just write it. Then dn3 x, 0, dn3 dy, 0, dn3 dy, dn3 dx. That's what the B matrix looks like. Again, it's just different derivatives of the shape functions with respect to either x or y. And I don't know what the first shape function looks like, but there is, for the linear triangle, you can just go and look what the different shape functions are, and you can take the derivatives. And actually, the derivatives are not too bad. I don't recall exactly, but for the linear triangle, if you go to previous notes, you can see, for example, the first shape function is 1/2 times the area, and then something, something, and then here there's like y2 minus y3 x plus x3 minus x2y, something like that. I'm not exactly sure this is correct, but something like that. That's what the first shape function looks like for the triangle. So if you take the derivatives, then actually the derivatives are pretty simple. So for example, the dn1 dx is probably just 1/2 area y2 minus y3 or y3 minus y2, something like that. And the derivative with respect to y is just x3 minus x2. So that means that, you know, you can go and get every single one of these entries. You don't have to do it because I have it in the next slide. But if you actually go to the shape functions of the triangle, take derivatives, and put them in the B matrix, what you end up with is this. So this is the B matrix for the triangle. So 1/2 times the area of the triangle, and then every one of these is just the difference. So y23 is just y2 minus y3. Then x32 is just x3 minus x2. So again, if you have a triangle, all you need to be able to do is get the area of the triangle, and then given the x1, x2, x3 coordinates, y1, y2, y3 coordinates, you can fill in all the entries of that B matrix. And given that, the actual stiffness matrix, I don't know if I have the actual stiffness matrix is just going to be the A of the element times this B matrix transpose times this D matrix that I don't think I have defined. Hopefully I have it in the next slides. I need to tell you what that is, times the B matrix. And again, you have everything. So the area is just the area of the triangle. The B matrix is whatever. This is going to be some numbers. Then the D and the B matrix again. I still have to define what this D matrix looks like. Anyone has the book here? the FE book. I don't remember off the top of my head, but it involves the Young's modulus and the Poisson ratio. So let me find that very quick. One sec. This D matrix depends on whether it's a plane stress problem or a plane strain problem. For 2D, if it is, I think I don't know if you've done both of them in the lab. Yeah, so it's in page 223 of the book. So for example, for plane stress, the D is Young's modulus over 1 minus V squared, and then 1 Young's modulus 0, Young's modulus 1, 0, and then 0, 0, 1 minus Young's modulus, sorry, Poisson ratio over 2. But this one is in the book, what I would provide. And then for plane strain, it looks a little bit different. I'm not going to write it down. But again, this D matrix is just basically material properties. It's related to the Young's modulus and the Poisson ratio. And the reason why it's not like the conductivity matrix is because this D matrix basically is what relates strains to stresses. So given the strain components, D times the strain components gives you the stresses. Questions? Cool. All right, so this is how you would calculate the stiffness matrix for the constant strain triangle. Again, the B matrix, all you need to know is the components of the nodes of the triangle and the area of the triangle. You can get the B matrix. And then the D matrix is, again, just some constant matrix that depends on Young's modulus and Poisson ratio. And then the force vector is the integral. I had done this before. So it's the integral of the shape functions times either X or Y. This is in particular if the body force is not constant. Should make a note here. So if B is not constant, but you have the B associated with the nodes, so if the body force is not constant, but you have the values of the body force at the nodes, you can use this formula. If the B is constant, I think probably what I would do, if B is constant, then I'll just do this and we'll end with that. Then you can imagine that this actually is just the area over 3, because the integral of the shape functions is just going to be the area over 3, and then bx, by, bx, by, bx, by. Again, if the b is constant, then the force vector is just area over 3 times bx, by, bx, by, bx, by. All right. I'll see you on Wednesday.